All right, welcome back, everyone. So I am Thomas Schön. I'm the Bayer Professor of Artificial Intelligence here at Uppsala University, and I'll be moderating this final session for today. So it's a great pleasure to introduce Christina Goldsmith, who is a professor of probability at the University of Oxford. So before that, she received her PhD from Cambridge and then did several postdocs, and now back in Oxford again. She is mainly interested in random discrete structures like trees and graphs, which is also what she will be talking about today. So please, Christina.
Good. Now I can hear myself. Very good. So as I was saying, thank you very much for this invitation. It's a huge honor. So I'm going to be speaking about one of my favorite mathematical objects, the Brownian continuum random tree. So let me show you what it looks like. So this is like many of the pictures in this talk by a very talented guy called Igor Kochemsky, who certainly people over there who know. So the Brownian continuum random tree was introduced by David Aldous in 1991, of course building on the work of many other people. And my aim in this talk is to tell you what it is and why it's interesting. So, roughly speaking, this is what you get when you take a large uniform random tree and you look at it from a long way away. So, I want to show you how it arises and something about why this limit works. And along the way, I want to give you a sort of flavor of my area of mathematical research, which is somewhere between probability and combinatorics, and also somewhere between discrete and continuous. I don't know if this thing is, am I in a strange position? It seems to be, if I pull it a little bit away from myself. Is that better like that? Or is that now not picking enough up? That's good. Okay, great. So, let me start by saying something about why we should study mathematical trees in the first place. So you all know what a tree is in nature, but the point is that they show up in all sorts of other places in the physical world, not just as the trees that we're very much aware of all around us. So here, for example, is a tree that's produced by applying a high voltage to a sheet of plexiglass, and you get one of these Lichtenberg figures, which are very beautiful. So I think you can see that there is some resemblance, at least from a distance, between these two things. Okay, here, for example, is a river network. Okay, and again, this is another place that sort of dendritic or tree-like objects appear in nature. And then there are other bits of science in which we come across trees. So anytime we try to classify things, we tend to come up with these tree-like things. And then, of course, the absolute classic family tree. So this is another instance in which we come across trees. Okay, and we also encounter trees whenever we try to describe networks. So networks are a hugely important area of study at the moment, and trees are somehow minimally connected networks. Okay, so in mathematics, in addition to this vast number of application areas that you can find in the physical world, in applied sciences, they also show up as a sort of ubiquitous structure within mathematics. So there's an entire area of mathematics devoted to the study of discrete structures, of which trees are an example. But they also tend to show up largely because recursion is such a fundamental notion within mathematics. And whenever you've got a recursion, there's somehow a tree sitting there. Okay, so mathematically, trees are simply a subclass of graphs. So what's a graph? It's a collection of vertices, along with a set E of pairs of vertices, which we call edges. So these are all of the graphs on 1, 2, 3, and 4 vertices. So let me try and show you what's going on. So here, for example, I've got 4 vertices, and I've got 3 edges, which join pairs of those vertices. Okay, so a graph is connected if I can get between any pair of its vertices by traveling along edges. So on this page, I've got examples of graphs which are both connected and not connected. So this one certainly is connected because I can get between any pair of vertices. And this one is certainly disconnected because I can't actually get from any vertex to any other by traveling along edges. So a tree is a connected graph that has no cycles. Okay, so I've picked out in orange here the examples of trees here. Okay, so these, I can get between any pair of vertices by traveling along edges, but I don't have any cycles. So if I were to look at this graph, for example, this one's disconnected because this guy over here isn't connected to the other ones. And this is a graph that has no cycles, but it's not connected. Okay, so I've excluded all of the ones that aren't either connected or which have a cycle. So sometimes when we're thinking about these objects, it's useful to give them a little bit of extra structure. So sometimes we want to choose a particular distinguished vertex as a root. So the terminology for these things often mirrors the terminology from nature. Okay? Sometimes we want to label things. Sometimes we want to choose a particular way of drawing things in the page. Okay, so I'm going to focus in this lecture on what I'm going to call rooted binary plane trees. So what do I mean by that? So I'm going to have a special vertex at the bottom, which is playing the role of the root, and it's always going to have a single edge coming out of it. Okay? Every branch point in the tree is going to split me into two subtrees. Okay, so every branch point will be into two. And then I'm going to care about the order in which I draw things in the plane. So let me... it's too tempting to use this blackboard. So let me draw two examples which I want to distinguish between. Okay, so these are two different... Oops. Two different trees as far as I'm concerned. Right, so the difference between them, you could think about sort of putting a mirror here and flipping the other side. And as far as I'm concerned, those are two different trees because I draw them in the plane differently. Okay, so the set of things I'm going to be interested in is this blackboard bold Tn. So this is the set of rooted binary plane trees that have n leaves. Okay, so let me just make some simple observations about these. So I've got n leaves. So what are leaves? Leaves are just these endpoints here that connect to nowhere. Okay. So every element of this set has n-1 internal vertices. That's these branch points here. Okay. Plus it's got a root, which I don't think of as a leaf for those people over there who work on these things. Okay, so the leaves are the ones at the top. The root is the one at the bottom. Okay, and it turns out that every element of Tn has two n-1 edges. So there are lots of things about these trees which are fixed if I fix my number of leaves. Okay, but there's of course the shape which can be different. Okay, and I'm going to not draw the dots because it's going to get tiresome to keep having them in. So just the points where these edges meet are going to be the vertices of my graph. Okay, so first, most basic thing you might want to ask is, how many of these things are there? Okay, and for n greater than or equal to 1, it turns out that the number of these rooted binary plane trees is given by this quantity here, 1 on n, 2n-2, choose n-1. So I've expressed that in terms of factorials. I hope that's okay for everyone in this audience. Okay, great. So that's how many of them there are. Okay, so these numbers are rather famous. These are the so-called Catalan numbers, so named after the Belgian mathematician Eugène Charles Catalan, who has this wonderful portrait, which I sort of needed an excuse to use in a lecture. Okay? And they turn out to enumerate an astonishing variety of different structures. Okay, so not just rooted binary plane trees, but all sorts of other things. So, in consequence, there are one-to-one correspondences between lots of the different things which were enumerated by these Catalan numbers. And I want to just kind of sketch out for you one of those one-to-one correspondences. So in mathematics, we call these bijections, and they're extremely useful for enumerating things. If you've got a class of object that you don't know how to count, but you know that it's in one-to-one correspondence with some class of objects that you do know how to count, then you can do your counting over here and transfer it back to your original problem. Okay, so let me give you a correspondence between rooted binary plane trees with n leaves and what I'm going to call lattice excursions of length 2n. So what do I mean by a lattice excursion? So this is an example of a lattice excursion. So it's a path that at each step is going to go either up 1 or down 1. Okay? And it's going to start and end at 0, and it needs to stay strictly positive in between times. Okay, so it's a path of length 2n made of ups and downs such that I say strictly positive except at the endpoints. Okay, so what's the recipe for getting between these things? So I'm going to show you first how to get from a tree to a lattice excursion, and then I'll show you how to get back again. Okay, and that will prove that this is a correspondence between them. So I'm going to start every excursion with a +1 step, and I'm going to travel around the tree from left to right, recording a step whenever I see a vertex for the first time. Okay? And if that vertex is not a leaf, I'll have a +1, and if it is a leaf, I'll make a -1. Okay, so let's do this. I'm going to start at the bottom. So the root is not a leaf, so I'm going to make a +1 step. This is, again, not a leaf, so I'll make a +1 step. And I keep making +1 steps until I encounter a leaf for the first time. And then I'm going to make a -1 step, and I'm going to continue exploring the tree at the next sort of vertex rightwards that I haven't yet encountered, which is this one. Okay, so this is not a leaf, so I make a +1 step. Then I encounter a leaf, so I make a -1 step, and another -1 step. Now +1, -1, -1, and so on and so forth. So you can see that as I travel around this tree, I'm drawing out my lattice excursion. Okay, so I hope that's at least reasonably convincing that I can get from my tree to a lattice excursion. Okay, and we can go back the other way. And in a way, this is even simpler. So I'm just going to draw in some lines into my picture. So what have I done? I've drawn in lines every time there are up steps, and I've drawn these horizontal lines across underneath the lattice excursion. And if I take away the excursion itself, what I get left with is a tree, which if you look at it sideways, so imagine rotating it in the page, that's exactly the same tree as on the right-hand side, just with sort of edge lengths which are slightly stretched. Okay, so that means that I can get back the other way again, so I can recover my rooted binary plane tree. So I think this is rather cute, and it's also something I'm going to make use of later on when it comes to trying to make sense of this Brownian continuum random tree. Okay, so if I want to know how many rooted binary plane trees there are, I can instead count lattice excursions. Okay, so let me at least give a sketch of how to do that. I'm not going to go through all of the details because it gets a little bit fiddly at the end. So the first thing to observe is that my excursion is going to make 2n steps, and the first and last steps are definitely going to be +1 and -1. So they're kind of fixed. I don't need to count how many possibilities there are because they're always going to be there. Okay, so I've really got 2n-2 steps to play with, and of those, n-1 have to be up, and n-1 have to be down, okay, because I need to end up back at 1. Okay, so among paths which are up-down steps of length 2n-2, there are 2n-2 choose n-1 ways to choose the positions of the up steps among the 2n-2 steps. Okay? And once I've fixed the up steps, the other ones have to be down steps. Okay, so that's how many ways there are of choosing paths which go from 1 back to 1 by making up and down steps of length 2n-2. And the problem is that some of those go below the level 1. Okay, and we want to just keep hold of the ones which stay at or below, sorry, at or above the level 1. And this is where I'm going to shove a few things under the carpet. So it turns out that the number of bad ones, the ones which do go below the level 1, is 2n-2 choose n. And if I subtract that off the total number of paths, then I get precisely this Catalan number that I was after. So how do I get this 2n-2 choose n? Well, there's a slightly fiddly argument involving reflecting paths and counting very carefully how many things go wrong. So I'm not going to show you that just because I think it would get a bit intricate. But anyway, that's at least a sketch proof of how we go about counting these things. Okay, so we have an explicit formula for how many rooted binary plane trees we have. And from looking at it, it's difficult to get a sense of what this looks like for large n. So let me use Stirling's approximation to give its asymptotics. Right? So this is looking like 4 to the n-1 divided by n to the 3/2 square root of pi as n goes to infinity. Okay, so in other words, we don't really care about this n to the 3/2 on the bottom. These are growing, the number of these things is growing exponentially in n. Okay? So I'm going to be interested in understanding what a typical element of this set looks like. Okay, so I've got these exponentially many trees, and I want to know what a typical such tree looks like. And to make sense of that mathematically, what we do is we pick one uniformly at random. So that's what I mean by a typical element of the set. Let me just pick each of them with equal probability and say that gives me a random tree. What can I say about its properties? Okay, so my aim is to understand what Tn looks like as n goes to infinity. So in principle, what I could say is, let's take a bag with all of our Catalan many trees in it, sort of reach in, pick one out uniformly at random and look at it. And the problem is that that's not a very practical way of doing anything. So either as a sort of thought experiment, or more crucially, if you were to try and simulate this thing on a computer, that's not something that's going to work. Okay, so it would be useful to have an algorithm for generating a uniformly random element of this set, so my Tn. Okay, unfortunately, one exists, and it turns out to be very simple. So this is an algorithm due to Jean-Luc Rémy, who unfortunately I don't have a photo of. I couldn't find him anywhere on the web. So this is a way of recursively constructing a sequence of trees such that Tn is uniformly random on my set of rooted binary plane trees with n leaves for each n. Okay, so not only does it do it for a single n, it does it simultaneously for all n. So it works as follows. I start from a single edge, and I'm going to label its endpoints just so I can see where they are. So they're going to be labeled 0 and 1. And then at each step, at step n greater than or equal to 2, among the thing that I've built so far, I'm going to pick an edge uniformly at random. I'm going to split it in two by putting a new vertex in the middle of the edge. I'm going to attach a new edge with a new leaf at its far end. And I'm going to label that leaf n. Okay? And I'm going to do that attachment, so with probability half to either side of the edge that I obtain, because I want to have a planar object at the end of the day. So let me show you in a series of pictures. So I start with this single edge with endpoints 0 and 1. Okay, I split it in the middle and insert a new edge with a new leaf labeled 2. So this is now a new vertex that I'm not bothering to put a dot on. And I insert this on the right with probability half and on the left with probability half. Okay, and then I'm going to repeat. So I pick one of these edges uniformly at random. It turns out to be this one. I insert a new vertex in its middle and a new edge to a leaf. And I continue. Okay. So you should interpret this picture on the left as being this tree here. Right? So I'm keeping the same ordering in the plane, and I've just drawn it in my sort of standard way of drawing these things. So the edge lengths in this picture on the left-hand side have no meaning. That's just so that I can manage to squeeze it on the page. Okay. So my claim is that for each n, if I forget the labels, Tn is a uniformly random element of the set that I'm interested in. Okay, so we've got a pretty simple mechanism for generating the set of objects that we're interested in studying. Okay, and the hope is that by analyzing aspects of this algorithm, we should be able to understand key properties of the objects. Okay, so what can I say about Tn as n goes to infinity? So the key idea here is that we should think about rescaling the edges of the tree. So let me go back to the previous picture. So it's natural to think of the edges in this picture as having length 1. Okay? So let's now think about them having length 1 on square root of 2n. The factor of square root 2 doesn't really matter. What's important is that I'm scaling like 1 on square root of n as n goes to infinity. So it turns out that if I want to make this object get more and more leaves, I want to look at it further and further away, the sort of the definition of further and further away for me is essentially just squish the object by a factor of 1 on square root of 2n. Okay? And if I do that, and we let n go large, then what we obtain is this Brownian continuum random tree in the limit. Okay, so in order to get an idea of why this is the case, I want to make a sort of detour via a collection of sort of classic probability problems involving balls in urns. So this is just a sort of mathematical formalism of a whole family of problems which turn out to crop up inside the Brownian continuum random tree. Okay, so let me tell you about the most basic of these urn models. So this is Polya's urn. So I'm going to start with one blue ball and one red ball in an urn. Okay, and I'm going to proceed as follows. I'm going to reach into the urn and pick out a ball chosen uniformly at random. Okay, and then I'm going to look at its colour, and I'll put it back in with an extra ball of the same colour that I just picked. Okay, so first go, I happen to pick a red ball, so I add in an extra red ball into the urn. Okay, and now I'm going to pick uniformly at random, and notice that because I've now got red balls, I've got a slightly higher chance of picking red now than I had at the start. Okay, and indeed, I pick a red ball, so I add it in with another red ball. Okay, so now I've got even a higher chance of picking red at the next step. So this is a process that has a sort of notion of reinforcement inside of it. Whenever I pick lots of balls of a particular colour, it becomes even more likely that I'm going to pick them again. Okay, but I've still got some probability of getting blue, and so blue gets a little bit of a catch-up in one step here. Okay, so let me let Bn be the number of blue balls at the nth step, and let's let Rm be the number of red balls at the nth step. And I'm starting with a single ball of each type, so B0 is 1 and R0 is 1. And notice that actually the sum of the number of blue and red balls at each step is just a deterministic quantity. I always add in one more ball at each step, so at step n I've got n plus 2 of these. So let me study the proportion of balls that are blue in this urn. Okay, it turns out to be a nice quantity. Okay, so how does Pn evolve? So suppose that at some particular step I've got proportion P of blue balls in the urn. So that means that, in fact, the Bn, I know that I've got n plus 2 in total, so my Bn is now n plus 2 times P. So if I pick a blue ball, which happens with probability P, right, that's the proportion of blue balls in the urn, so that's also the probability that I pick a blue ball. Okay, so what happens in that case? If I pick a blue ball, well, I'm going to add an extra blue ball, and then in order to get the proportion, I need to now divide by the new number of balls in the urn, which is n plus 3. Okay, so then my new value is this thing here. And on the other hand, I might have picked a red ball, and that happens with probability 1 minus p, so that's the proportion of red balls in the urn. And in that case, I just don't add anything to the number of blue balls. So I have the same number of blue balls on the top, but divided now by one more ball in the urn. Okay, so on average, what do we get? We get the probability of picking a blue ball times the resulting proportion in that case, plus the probability of picking a red ball times the proportion that I get in that case. And if you do the sums here, what you end up with is P. Okay, so given the value of Pn, so given the value of this proportion at step n, if I look at the average value at the next step, it's the same as my current value. Okay, so this is the property that we call a random sequence that has this property is called a martingale. Okay, and these are an absolute key tool in the analysis of stochastic processes. Okay, so the concept was originally introduced as a betting strategy, as so much of probability originated in sort of betting games. So in gambling in the 18th century France, but really the mathematical footing of these things was started by Paul Lévy, and in particular the convergence theorem that I'm about to use is due to Joe Doob. So this martingale Pn has one extra property, it's a proportion, right? So it's taking values between 0 and 1, and this boundedness is particularly helpful. So let me try and give an idea of what's going on here. These processes are nice because they're quite constrained. So the fact that my expected value at the next step is the same as where I am currently tells me there's not that much room for maneuver. And in principle, that means that these things have the possibility to converge as n goes to infinity. And indeed, that's what's happening. So this martingale that I've just told you coming out of Pollier's urn, bounded between 0 and 1, and it converges to a random limit. Okay, and in fact, we can work out what the distribution of that random limit is. So a quick calculation shows that for each fixed n, actually this proportion of blue balls in the urn turns out to be uniformly distributed on the set of possible values it might take. So, okay, let's start at step 0. So there we know that we've got proportion 1/2 of blue balls, and that's the only value in this set. And at each subsequent step, okay, we might have 1 on n plus 2 as a proportion of blue balls. So that's, we only have the original blue ball and none others. Or, alternatively, it might have been that we picked blue balls at every single step. We got as many as possible, so that would be n plus 2, because there's always the one red ball. And in fact, any of the values in between, they all have the same probability. So we've got a uniform on a sort of approximation to the interval 0, 1, so it maybe shouldn't be too surprising that when we take the limit as n goes to infinity, what we end up with is simply uniform on the interval 0, 1. Okay, so we've started off with a proportion a half of blue balls, and we've ended up with something which could be anywhere in the interval 0, 1. Okay, so the idea, really, is that sort of what happens early on has quite a large influence over the limit of this process, right? If it just happens to be the case that we picked a lot of blue balls at the start, then we're going to end up with a proportion that tends to be quite high. And if, on the other hand, we happen to pick lots of red balls, then we'll end up with a proportion of blue balls that's quite small. So those early steps of the process actually have quite a large influence. Okay. So martingales are magic. This is the message of this slide. Okay. So that was a little bit of a detour via one of the most famous models in Earn theory. And I should say that there's at least one expert on this in the audience, so I'm a little intimidated standing here. But anyway, so if I come back to Rémi's algorithm, okay, so we were recursively constructing a sequence of trees which had the right distribution. So let's just recap how we did that. We started with a single edge between vertices labeled 0 and 1, and at each subsequent step, we picked an edge uniformly at random, inserted a new vertex in its middle, added a new edge to a new leaf, and then did that with probability half either side of the edge that we picked. Okay, so let's think about how the distance between the vertices labeled 0 and 1 evolves. Okay, so that's a thing that we can get our hands on quite easily. And it turns out that this is actually somehow a typical distance in this object. Okay. So let's think about how this evolves. Okay, so the total number of edges that we have is 2n minus 1. Okay. So the number of edges in this path between 0 and 1, so if we add the new leaf somewhere along this path, then what happens is we split an edge into 2 edges, and so this distance gets longer by 1. Okay, and if, on the other hand, I pick an edge that's somewhere off of the path, so not between 0 and 1, then I'm just adding this length, this extra edge, or in fact extra 2 edges, because I split an edge into 2, and then I add an extra edge. That happens somewhere else. Okay. So equivalently, what I'm looking at is actually an Earn process. So let's imagine we've got blue balls and black balls. Black balls are going to represent edges in the path that I'm interested in between 0 and 1. Okay? And white balls are going to represent edges somewhere else in the tree that I don't care about. Okay, so if I pick a black ball, so that's equivalent to choosing an edge along the path between 0 and 1 to attach to, then the effect on the length between 0 and 1 is going to be to increase it by 1. Okay, so what I'm going to do, sorry, it's going to be, yes, I've done this wrong. So what have I done? Oh no, sorry, this is the original ball going back, yep, so I increase it by 1. Okay, so I add a black ball, and I'm also increasing by 1 for the white balls because I'm also adding an edge which is not on that path. Okay, so I add 1 extra edge along the path and 1 extra edge off the path. Okay, so that's 1 black ball, 1 white ball. On the other hand, if I add an edge somewhere off the path between 0 and 1, I'm just adding 2 white balls. Okay, so these are the rules for this little Earn. And I'm always starting with a single black ball. I'm always starting with a single edge between 0 and 1. Okay, so a more complicated martingale analysis than the one we did for Polyer's Earn turns out to show that this time, this distance between 0 and 1, so this number of black balls in the Earn, is in fact scaling like the square root of 2n. Okay, and indeed that we get some random limit here, which has a nice explicit probability distribution, the so-called Rayleigh distribution. So this is something that turns up quite often in physics, this distribution. Okay, so where are we? We've just seen that the distance between 0 and 1, as I let n goes to infinity, so that scales like the square root of 2n, which, with a nice limit. Okay, so that's one bit of the tree that I've managed to pin down how it behaves as n gets large. Okay, so what about the distances to the other leaves that I put labels on. Let's think about how those work. So, for example, let's think about the distance from the leaf that I labeled 2. So this is just the second one that I introduced in Remy's algorithm. That's why it's carrying this label 2. Let's think about its distance to the path between 0 and 1. If I can do that, then what I've picked out is effectively a sort of Y-shaped subtree where hopefully I can understand each of these lengths. Okay? And if I can do this repeatedly, then what I'm getting is actually a sequence of kind of approximations to my final tree. So if I can do this, say 3 comes here, and then 4 comes here, if I can keep doing this, essentially what I'm getting is a finer and finer approximation to the object that I'm really interested in. Okay, so the second step of Remy's algorithm, we've always got this picture. I mean, it might be that the vertex label 2 is the other side, but in terms of how many edges we've got, there are always 3 of them, and they're always in this kind of Y-shaped form. So the important thing here is that each of these 3 bits I can look at separately. There's sort of what's going on in this part of the tree, what's going on here, and what's going on here. And each of those is behaving like a little version of the original process. Okay? So if I just look at what's going on in one of these subtrees, what I'm seeing is a little version of Remy's algorithm, just restricted to a particular subset of the vertices. Okay, so the numbers of leaves that I add between these 3 different subtrees are, of course, dependent. Right? If I add more leaves up here, I'm going to get fewer leaves down here. But if you tell me how many leaves there are in each, then what I'm really seeing is just a little copy of Remy's algorithm. And so in particular, what I'm getting is a little rooted binary planar tree. Okay. So here I've drawn it sort of a little bit more carefully with 3 colors corresponding to the 3 trees, picking out the bits that you can see. So let me make an important aside. If you're willing to believe me that this thing possesses a limit, this tells us something quite important about it, which is that I can split a Brownian continuum random tree into 3 little Brownian continuum random trees where I've sort of randomly rescaled their sizes. Okay? And in particular, that tells us that this is a random fractal. Okay? It contains little copies of itself which have just been sort of scaled. Okay? So let's think about the number of vertices going into each of these 3 little subtrees now. Okay? So this is really much more like a sort of variant of the original polyazone that I told you about. So I've got 3 colors, 1 for each of my subtrees. Okay, and what's the rule? Well, whenever I pick an edge in one of these subtrees, I'm just going to add 2 more edges to that subtree. Okay, or equivalently 2 vertices to that subtree. Okay, so this is an urn where the sort of replacement rule is if I pick red, I put back in my red ball along with 2 more. If I pick green, I put back in a green ball along with 2 more, and similarly for blue. Okay, so by analysing this urn, I can understand these limiting proportions of leaves or edges or vertices which end up in each of these 3 subtrees. Okay, so I can even tell you by doing that what the random scaling factor that I need to apply to my little trees is in order to get back my big tree. Okay, so via urns, and using this idea of self-similarity, I can get at the limiting distances between the vertices labeled 0, 1, 2. I can do sort of versions of this analysis at sort of every scale I like here in order to get the distances between the vertices labeled 0 and 1, 2 up to k. Okay, and as I say, we want to think about these as sort of a sequence of approximations to some sort of limiting object. Okay. So, what's the limiting version of this process? So, this is Aldous' so-called line-breaking construction of the Brownian continuum random tree. So there's a first paragraph here, which if you don't know what an exponential random variable is, won't make much sense to you, but don't worry. I just want to say that there is something explicit here that I can write down, and these are things that we can sort of deal with very easily. But if it doesn't mean anything to you, don't worry. The picture is the important thing here. So what I'm saying is I'm going to take independent, identically distributed exponential 1/2 random variables, and I'm going to define a sequence of points which are increasing by summing up the first I of them and taking the square root. Okay, so what's the thing one can do? So what does that do? That gives me a sequence of random points on the positive real line. Okay. And as it turns out, these points are getting sort of distributionally closer and closer to one another as I go further right. Okay, and that's going to be a useful property. Okay, so I'm going to chop up the positive real line into line segments at these points. So imagine just taking a pair of scissors and chopping at each of these black points. Okay, so the limiting version of Rémi's algorithm then proceeds as follows. I'm going to start with this first line segment, which has length C1, and then inductively what I'm going to do is I'm going to take the subsequent line segments and just glue them to what I've already created at a position chosen uniformly at random over the object I've already made, choosing with probability half whether it's left or right. Okay, so let's do that. So, I have somehow lost my original line. That's very strange. Imagine there's a vertical line here which represents the original line segment, which for some reason has become invisible. Okay, so this in principle ought to be the second line segment, which is connected to that first one. Okay, and I'm just attaching these uniformly at random over the object, which is now bizarrely disconnected because it's missing its backbone. I'm sorry about that. I'm not sure what happened with my simulation. Okay, so the idea is that if I do this for k steps, I'm getting precisely this kind of k approximation to the limiting object that I want. Okay, so there's a completely non-trivial fact here, which is that if I keep doing this forever, this thing stays nicely bounded in the plage. Right? So in principle, by just adding more and more line segments, I could sort of disappear off to infinity somehow. And it's a theorem that you don't do that this thing remains compact. Okay, and that gives one construction of the Brownian continuum random tree, up to a small technicality that I won't talk about. Okay, so we have an object that we can get our hands on. Why on earth has it got the word Brownian in its name? Okay, so there's no Brownian motion visible in this description. Okay, so in order to understand the name, maybe we'd better first know a little bit about Brownian motion. So the Brownian motion is named after Robert Brown, who was studying the movement of pollen particles in a fluid. But really, in terms of the mathematical theory of Brownian motion, there were lots of people involved, but three of them were Bachelier, Einstein, and Smoluchowski. Okay, so let me start with a simpler object. So suppose we take a random walk. So this is like the lattice excursions that I was talking about earlier, except it has fewer constraints. So all I'm going to do is I'm going to start from 0, and at every step I'm going to go either +1 with probability half or -1 with probability half. And what I end up drawing is a picture that looks something like this. So at every stage I'm just choosing with equal probability up or down. Okay, so if I think about the position of this walk at a fixed time n, okay, so that's just the sum of n independent random variables, each of which is +1, -1 with equal probability. So that's got mean 0, and indeed the Wn has variance n. Okay, and then the central limit theorem tells us that we can understand the limiting distribution of that quantity Wn when I rescale by square root of n. Okay, so it tells us that this distribution of this object gets closer and closer to the standard normal or Gaussian distribution as n goes to infinity. Okay, so that's for a fixed time n that I'm letting go to infinity. So we're saying that essentially Wn is going to be on the order of square root of n, and when I rescale by that square root of n, I'm getting something which is a standard Gaussian. But I can do this simultaneously at every time point. Right? So what I'm going to say is let's take this walk at time point integer part of n times t, where t is just some positive time, and let's think about sending n to infinity now. And I want to do this simultaneously for all values t. Okay, so Donska's theorem says that in this case we get a Brownian motion in the limit. So this is a random process which at every time point has a Gaussian distribution, but of course it's got particular dependencies between different time points. Okay, so comparing to our random walk on the top, this is what a Brownian motion looks like. Okay, so this is a process that every fixed time has a Gaussian distribution and particular covariance structure. Okay, so at the start we had lattice excursions, right? And we were really just thinking about enumeration at that point. But we've now got to the stage where we're picking our random binary rooted plane tree. I'm getting too many words in the wrong order there, but we're picking our trees uniformly at random, right? Uniformly from the set of possibilities. And of course, because I've got a correspondence here, if I pick the tree uniformly at random, I'm actually picking the lattice excursion uniformly at random from among the possibilities. Okay, so another way of doing that, so in fact, we could even find the tree inside the lattice excursion. So if we take the tree to be uniformly random, the lattice excursion is also uniformly random. And the point is that that's the same thing as one of these simple random walks, except that I've just forced it to stay positive and come back to 0 for the first time at time 2n. Okay, so I've just conditioned my random walk to do something a little bit weird. Okay. Well, if I rescale time by 1 on 2n, and space by 1 on the square root of 2n, then by analogy with the random walk, I'm going to get convergence to something which ought to be a Brownian motion that I've done the same conditioning to. Okay, and I'm going to shove lots of technical details under the carpet here because this is not a completely trivial thing to do. But what we end up with is an object which is essentially a Brownian motion conditioned to stay positive until it comes back to 0 for the first time at time 1. Okay. So if we start with our lattice excursion, then we should have as a scaling limit, if we do this correct rescaling, we get a Brownian excursion in the limit. Okay, so how do I get back from a Brownian excursion, or an excursion function in general, to a tree? So imagine taking your excursion, this is a bit of a caricature here because I can't draw Brownian motions very well. Imagine taking a glue stick and putting glue on the underside of this function. Okay, and then what I'm going to do is I'm going to squish the two sides together. And when the two parts that have got glue on them meet, they stick. Okay, and in this way I'm going to form a tree. Do you believe me? Seem plausible? Okay, so let's do that bit backwards just so you can see what's going on. So these kind of local minima in this function are turning into branch points in the tree. Okay. So you can do that to any continuous excursion function that you like, and indeed you can do it to a Brownian excursion. So if I do it to the Brownian excursion, what I get is a Brownian continuum random tree. You won't be surprised to learn after all of this time. What about if I do it to my little lattice excursion here? Well, it turns out I don't quite get the same tree, right? So we had a particular tree that was associated with this excursion, which is this one on the left here. If I do my gluing operation to this lattice excursion, what I get is actually this tree. Okay? And they do look sort of a little bit similar to one another. And the point is that for large n, if I'm considering this idea that I'm rescaling edge lengths by 1 on square root of 2n, so any individual edge is not really going to figure in the limit. In fact, these are kind of close enough that actually they'll be indistinguishable in the limit. So the tree I get from gluing the Brownian excursion is the Brownian continuum random tree. The tree that I get from gluing my lattice excursion is kind of close enough to the tree that I'm after that I can't tell the difference. And so, at least heuristically, I get convergence of one to the other. Okay. So, how am I doing for time? Not too bad. So, let me just say a little bit about the properties of this thing. So, have we seen it's a random fractal? It's got little copies of itself within itself. Okay. And it turns out to have fractal dimension 2, which might be surprising to you, given that we've got one construction of it which can simply consist of gluing line segments together. Okay, so in principle, that's a one-dimensional object, and indeed any of my kind of K approximations to the object is one-dimensional. So there's some interesting stuff happening then in the limit, and part of that I shoved under the carpet. Okay. Despite its complexity, we can actually describe very explicitly various distributional aspects of it, which is kind of surprising and magic. And maybe just to say something about my work, because really none of this so far has been anything that I've done. One of my small contributions to this theory in joint work with Marie Albank has been to show that the Brownian continuum random tree is the unique fixed point of an operation which is associated with this splitting into 3 thing, and indeed that that fixed point is attractive. Okay, so in this lecture I've focused on a particular model of random trees, Okay, we took these random uniform binary rooted plane trees. But it turns out that as long as you choose an essentially uniform model of trees, uniform on some set of trees, you have to try very hard to get away from the Brownian continuum random tree in the limit. So this is the property that we borrow the word from physicists of universality. Okay, so the small-scale details of the model really don't matter that much. Okay, as long as you've got roughly a kind of uniform collection of trees, what you will get if you rescale in this kind of square root, 1 on square root of n sort of way is the Brownian continuum random tree. Okay. And the Brownian continuum random tree also shows up as a sort of building block, because in any model of graphs, if you take the connected components of your graph, any connected component of a graph has a spanning tree. And it's often useful to think of a connected component of a graph as a spanning tree plus some extra edges. Okay? And it turns out that the Brownian continuum random tree turns up, therefore, as a kind of aspect of the scaling limit of various graph models. Okay, so here are some of them. So the first couple of these are things that I was involved with. So I don't know if Svante is going to he's going to talk about critical random graphs of some variety or another. So this is a figure from some joint work with Nicolas Broutin and Luigi Dario Berri, in which we looked at the critical Oeder-Schwenyi random graph, where the critical components turned out to be very closely related to the Brownian continuum random tree. And that led on to some work about the minimum spanning tree of the complete graph with random edge weights, where again the Brownian continuum random tree is kind of sitting there in the background. And then there are these much more exotic-looking objects, which there are certainly people in the audience who've looked at. So this is the so-called Brownian map. So this is an interesting quotient of the Brownian continuum random tree, not that you would know it from looking at it, but this is the scaling limit of a, say, uniform random triangulation of the sphere. You get this extraordinary-looking object. And similarly, if you do that to a double torus, you get an even more exotic-looking beast. Okay. So this is a good moment to mention Jean-François Le Gall, who's another figure in the development of this theory of continuum random trees, or random real trees, as sometimes we refer to them. Okay, we can get beyond the Brownian CRT, but we have to do something a bit different. We have to move outside of the class of uniform trees and think about trees which are somehow inhomogeneous in a fundamental way. Okay? And there are other universality classes which have now been identified, and I'm just going to show you some nice pictures of what these things look like. So these are various of the stable trees. Again, pictures by Igor Kochemsky. So you can see there are many weird and wonderful different behaviors here. Okay, so I think that seems like a good place to stop, and thank you very much for your attention.
Thank you so much, Christina, for a beautiful lecture. Not only the pictures, but also the flow. I think you did a super pedagogical. You actually gave me a few ideas. I have a few questions, but I'll see what else we have here before I ask you a few things. We will also have a technical break, I think, for a few minutes, because you people at home are not really following right now. You will hear this in a minute or so, I think. So that's why we will have a break. But let's see, are there any questions?
Thank you very much. It's so rarely that you are in a talk and you understand almost everything.
Oh, thank you.
No, about this equivalence stuff, I didn't know that this thing was uniform as the red and blue balls, that turned out uniformly. But my association was if you construct the random number between 0 and 1, and you flip a coin, and heads means decimal 1 and tails means decimal 0, then you get in the limit the uniform number. And I guess
I think this is the same. This is,
that's
I mean,
the blue
it's all
and the red.
Diffinetti's theorem in some sense. If
Yeah.
that's the right way
So
to-
if it's blue, it's 1, and if it's red, it's 0. And
Yeah.
the same again. The first few results determine where approximately you will
going to
end
end
up.
up.
Yeah. So that was how I understood that proof. Yeah. Thank you.
You're very welcome.
Any more questions? Otherwise, let me ask before we have a break. So a while ago, 3-4 years ago, I was talking to friends in biology, and we were looking at trees, so phylogenetic trees. And questions they are interested in is like, how often does this happen, which is a speciation event when we have a new species? And what are the times in between? And then we have some evidence, so we measure some of the leaves, but not all of them, some of them. And from that, we need to reconstruct the tree and find these times, which doing the inference on that is nothing closed form, so we need to approximate. So we do things like one of your colleagues on Odyssey, like sequential Monte Carlo methods on these objects. And then we need to propose trees. And so we could do things that were biologically interesting, but what bugged me was I could not come up with a good way of suggesting trees that could be interesting to look at. So based on your, what you discussed in the beginning, these bijections that you have with the excursions, the lattice excursions, does that exist also for more complicated tree structures where you have different distances and?
Yeah, so I mean, these bijections are rather special. I mean, there's an entire kind of subfield that's concerned with trying to find them, if I can put it that way. And sometimes it works, and sometimes nobody can figure out how to find one. So I mean, these Catalan things are very special in the sense there were lots of bijections between different classes of object, and it was for that reason that I chose them. Actually, I took the kind of simplest thing I could find. But yes, I mean, one can use these kind of bijections more generally. I don't know if there's one that's sort of specifically kind of useful in the setting that you have in mind, but I do know that, I mean, Aldous has some work on phylogenetic trees in particular, sort of building on some of this type of stuff.
Yeah, good, thanks. Any more questions? Oh, there's one up there.
Okay, so this may be a bit more technical. You talked about this process, the Renyi construction, where you get a sequence of binary trees and then they converge to the Brownian tree. So, but what happens, can you get kind of functional convergence here to a process of, say, Brownian trees or Brownian excursions, wherever that evolve? I mean, if you do this for, say, n and for 2n steps, and then you let n go to infinity and look at a pair of them.
Yes, I think so. Although I'm blanking slightly. So, I mean, Luigi has in particular thought quite carefully about this, and I can't remember where exactly it went, but yes, I think one can. I mean, so these Remy trees are kind of special in that we've got a good coupling between different values of n. I mean, so the analog of this story in general works in distribution, but this is the situation where you get really almost sure convergence to the Brownian CRT. And so that's rather special, and the coupling is
yes,
kind of
that's why I asked the
question.
question.
The reason why this might actually work, yeah. I need to think a little bit further about what the actual correct answer to your question is, but yeah, certainly people have thought about it.
Okay, thank you.
So it's a great pleasure to introduce the next speaker, who is Svante Jansson. Svante is a professor in mathematics here at Uppsala University. He received his PhD the same day you turned 22, I think,
yes.
Which is impressive. Yes. And then you went on and you did another PhD, and then you moved to Stockholm and stayed in Uppsala.
That was only for a year in Stockholm. But
for a year, and then in Chicago, I guess.
That was half a year, yes. But basically, I've been in Uppsala.
And then you came back.
Yes.
We're glad for that. So please,
yes.
Thank you.
Okay, thank you. Yes, so I've been here a long time in Uppsala, and one of my main interests is just like Christina is a study of random discrete structures, and in particular limit for them asymptotics when the size goes to infinity and when the limit turns out to be some kind of continuous continuous random structure. And very often that continuous limit is some version of Brownian motion or so. So I will not talk about the Brownian tree that Christina has talked a lot about. Instead, I'll mention some other related problems where we also get Brownian motion and things connected with that. So I choose to talk about random graphs which is one of my favorite areas. And Christina mentioned graphs before. So graphs, also called networks, especially when dealing with applications. It is basically just you have a number of vertices, and so I'm interested in limits. So think of these numbers being very large, not just a few millions or so, but very large and going to infinity at the end. And then we have some edges drawn here in some way. And I'm interested in random graphs where we draw these by some kind of random procedure. And that can be done in various ways. But today I'll now just talk about the simplest version, which actually Christina showed a picture of, the Erdős-Rényi, where we construct this random graph just by taking for each pair of, well, we denote it, standard notation, G and P. N is the number of vertices, we start with them, and then P is some probability between 0 and 1. And for each pair of vertices, we just decide randomly. With probability P, we put an edge there, and with probability 1 minus P, we don't. So you can say we just flip a coin. We have a coin where we get heads with probability P, and we flip the coin, toss the coin for each pair of vertices, and then sometimes we get heads, and then we draw an edge, and sometimes we don't, and then we don't draw anything. So that will give us a huge random graph. And this was studied by Erdős and Rényi a long time ago. Was well, when I was a child, before I even started university, 1960 was the main paper on this. And one of the things they did was to look at question whether there will be, this graph is connected or not, as Christina talked about reason. And moreover, what's interesting here is situations somehow like this, where it's not completely connected, but you have one big connected set, and then you may have some, typically you have some small pieces outside it. So in this case, we say that we have a giant component. So in this case, it's this thing here, it's a giant. And what they found is that that is typically is the case if we have enough edges that there is one giant component and then maybe some small components outside. And that's something that since then have been found to be, say, typical in very many different types of random graphs. We construct random graphs in different ways. I mean, I work myself on various other types of random graphs, and so have many others. And this is what we expect, that it will look something like this. But let's look at just this G and P thing. To be more precise, what they showed was that we scale this now. I mean, n goes to infinity. We scale probability. We take some constant lambda. So lambda is a constant. Probability is lambda over n. That turns out to be the right scaling for this to be very interesting. And if what they showed is if lambda is less than 1, we have no giant component. And if lambda is bigger than 1, we have, I mean, with very large probability, we have a giant. And they even have a formula for how big it is. I mean, it will be roughly, well, a certain constant times n vertices in the giant. And there's a formula here which turns out to be 1 minus rho is equal to e to minus lambda times rho for this lambda. So I want to quickly describe why we get such a result here, and connections to Brownian motion. So let's suppose that we are given this graph now. It's random, but and maybe we don't really know what it looks like. We don't see the edges yet. They are hidden for. We try to see if there is a giant component or not. So we start by picking a vertex, this one, say, for example. Take a. Okay, and now we check, do we have any edges and where do they go? In this case, we have just one edge, so we follow that. Now we see, are there any more edges? No. Okay, that means we found small component, there's nothing more to be done, so we pick the next vertex. Maybe we pick this one, then we unlock again. Then maybe we pick this one. Okay, so now we start, follow all edges from it. In this case, there are 3. Okay, and then we take one of them, this one, for example. We follow edges from that, and so on. And we follow edges, and eventually we'll find this component here. In this case, this was a very large component. Let's see now what this exploration procedure, how that works as a random procedure. One way to think of this is as a branching process. I mean, we start here with one vertex, and I don't know anything else about the graph. I haven't seen it yet. So I look at the number of edges from it. It's random, and with this thing, I mean, there are n-1 other vertices it can go to. For each one of them, I have probability lambda over n. So the expected number is, well, n-1 is almost n here, n is large, so expected number is lambda. More precisely, it's a binomial distribution, n-1 and lambda over n. And we know that when n is large, this is roughly a Poisson distribution with parameter lambda. So we can say, approximatively, we get the Poisson number of children here. In this case, it was 3. And now from each one of these, we do the same thing, and we look at how many neighbors we have, and that's almost the same for each one of them. So we get almost new random numbers which have the same Poisson distribution. Now I forget about that figure, here's a new graph. So maybe we'd get no one there, and maybe 2 here. And then we go on generation after generation, and maybe it dies out quickly as it did in these cases here with just one or few generations, or maybe it will grow and we will find a very large component. And this is a typical structure, what we probably call a branching process, more precisely a Galton-Watson process. And then it's a very old, well-known fact that if this expected number of children each time lambda is bigger than 1, we will, at least with reasonable probability, get something with large exploding here. If lambda is less than 1, it will die out very quickly. And at least the last thing is easy to understand, because the expected number in the first generation is lambda, then the expected number in the second generation is lambda squared, and the third generation is lambda cubed. Do you hear me? Okay. And so on. And if lambda is less than 1, that rapidly converges to 0. In the opposite direction, if lambda is bigger than 1, we see the expected number go to infinity. Then you still have to do some work, but at least it's reasonable to explode. This is something that has become widely known to the general public during the last 2 years because of the COVID pandemic, because this is essentially the same thing that happens when we have an infection that spreads. In that situation, lambda is often called R0, the expected number of new people that each infected individual infects. Therefore, I mean, a lot of interest whether that number is bigger than 1, and then we expect the epidemic to grow, or if it's less than 1, and then the epidemic will die out. So we have precisely the same phenomenon here in a more, say, clear-cut, mathematically clean situation. That is why we get precisely these 2 different cases, with lambda less than 1, bigger than 1. Let's look at this in a slightly different way to see the connection Brownian motion. Instead of doing whole generations at a time, let's do this more slowly and just explore one vertex at a time. So we have the same situation here. We start with just select one vertex at random, and we get its neighbors, children. There are 3 here, say. And then we, well, take a new color, red here. Then we find the 3 children. Okay, we pick one of them first. and we see how many children we get. Well, in this case, just one, so we go there. And then we take the next one, in this case, maybe this one, and then this one we go here, and maybe from that we get children here. And it really doesn't matter which order we do it. Now I do it in what's called depth first order, but that's not essential, and so on. And when we do this, we can, when I'm up here, you can see we have a lot of vertices we have found but haven't had time to explore yet. This one and this one and this one, for example. So we can say we keep a stack, to computer science language here, of active vertices. We've found them and we have to investigate how many children they have, but we just haven't had time to do it yet. And if we keep track of how big this stack of, say, active vertices are, then we can say it's a queue of vertices that's waiting to be checked. Investigated. Let's say the Q1 is the number we have first time. So in this case, Q1 is 3. And Q2 next time, well, then I get one new child, but also this one is now checked already, so I lose that. So I get 3 again. So this is Q1 plus, let's say I get, this name was X1. This is X2 is number of children there. This is X1. This is Q plus my X2 minus 1, Q1, and so on. And what happens is that I get, in general, I get increments of, so Qn is, well, I just say Q3 is Q2 plus X3 minus 1, where X3 is the number of children of the third one investigated, so on. Except that in some case, when I have completed a full component, then I just have to start again at some other point, and then I don't have this minus 1. And the point is that these x's are now independent random variables with this, approximately we begin with this Poisson distribution. So this will be like a random walk. And we know a lot about random walks, and they will look more or less like this random lattice path we saw before. Not precisely, but very similar. And what happens in this case is that we, let's think of this. We get a picture like this. If time, here we have time now, number of steps, and let me scale it by n, and here is the size of this walk. If lambda is bigger than 1, the expectation of x minus 1 is positive. We'll get something which is roughly linear in the beginning. But then something happens when, because I lied little, these are not precisely the same, because I start using up vertices. And when I've already investigated half of the vertices, then there's only n half vertices left to check. So that means I'll tend to get fewer and fewer new children. So therefore, actually, if we do calculations, the mean will then go down, and at some point we'll hit 0, and so on. So this is typically what will happen with this QK, and here it's divided by n also. And this, if we interpret this, it means, that when we hit 0, that means that we really have to start again a new component. This will be the size of the big component we have found. And actually, it will satisfy this equation if we do the calculations here. But now comes the Brownian part here. Here I've just made a deterministic approximation with a mean here, which is a good first-order approximation because of law of large numbers, because I add very many independent random variables here, and remember that n is thought to be extremely large. But actually we know that it still is random, it's not precise, and the second-order fluctuations here are given by central limit theorem, or rather by Donsko's theorem that Christina mentioned. So it will actually, this Q thing will actually look like some kind of, think of a Brownian motion, some Brownian fluctuations around this deterministic curve. And then, well, we may actually get some negative first. That just means precisely as did before. We happen to start by looking at some small components, but that will happen only a few times. Then we are in a big component, it doesn't really matter, it's oscillations, until we hit the end. And these oscillations here, think of this as a Brownian motion, which you saw a better picture of before. And one conclusion we can draw here is, I said here, this is roughly how big it is, but let's see a second order thing. So the size here is determined by the precise point where we hit the axis. We hit 0. So here we have roughly a linear part with a essentially deterministic point, but we actually have some random fluctuations which are a Brownian motion, which means they are like normal variables. And this curve is linear now, no small scale here, okay, approximate linear function. So small oscillations, vertical direction will translate into corresponding horizontal oscillations of the hitting point, which therefore will be normal. So actually we will from this get a normal limit. If we are more precise, standard deviation of order square root of n, one can compute the variance zone. So I should say that this, as I said, this was Erdős and Rényi original paper was in 1960, but this fact with giant or no giant has been there's been given several different proofs by many different methods after that. This fact with normal limit has also been proved several times. I think first one was Stepanov in 1970, and Pittel and Wormel after that. And this proof with Brownian motion like this was by Bolobash and Riordan about 10 years ago. And let me also say what happens in the, quickly, here I said less than 1 or equal or greater than 1. But what happens in the critical case if lambda is equal to 1? Let me just say quickly, then we have a curve which looks like this. The mean will be negative, go down. But actually we still will have some random fluctuations just like here. So we can get some components in the beginning here. And what happens in that case is that one should do another scaling. So in that case, turns out right scaling is divided by n 2/3 here and 1/3 here. And then we will, this Brownian motion will be of the same order as this curve here, Brown fluctuations, and we can find components now, meaning in this case excursions where they stay positive or more precisely stay above its previous minimum. This was something which David Aldous did in another paper. We heard about Aldous before. This was another big result of his, also from the 90s, that the excursions of this Brownian motion will describe how the largest components will be here. They will be of order n or 2/3, but they will be more random in size than in this case here. So these are examples of how Brownian motion pop up. And as I said, this happens also in other, very many other models of random graphs. So I will not go into more details about this here. Just mention these are old results, what I've said here. I haven't done myself, others have done them, but I'm right now working on a study, writing a paper on the depth first search in a certain random directed graph where we have precisely the same type of behavior. This was inspired by a question of Donald Knuth in connection with a book he's still writing on. And I actually, this is very recent, I wrote some of the proofs yesterday. But I should also say again that I mentioned epidemics before, that mathematical models of epidemics are very often done using random graphs. And you have, as I said, same type of behavior there. Without going into details, you maybe want to make it a little bit more complicated, but even if you take simplest mathematical models for epidemics, you have the same type of behavior. And then, for example, Frank Ball has shown that in some simple model you get precisely the same kind of thing with some normal limit again of the total number of infected for precisely the same reason as in this picture here. Okay.
Thanks a lot, Svante. Thanks a lot. So let's see if there are any questions. I guess we all know how to relate to lambda here now in a painful way. I think there's time for one small question, perhaps. We also have a discussion afterwards where we can talk more. I can ask a super detailed question, but in this case, you said you reach a normal distribution when you cross. Why do you do that?
Because of, if you first look at this sequence of Qs here, if you take a Q at some fixed point here, it is a sum of a large number of independent variables. So by central limit theorem, it has a normal distribution. Right. And then now you go on, if you look closely what happens, close to the crossing point, you have here, let's say, here's the mean. Now here's same thing in larger scale. There is the expected value, but actually you have some a little bit larger here, and that means you will actually hit a little bit later. So therefore it is just a linear transformation from vertical to horizontal fluctuations.
Thanks. Thank you. All right, let's thank Svante again. Thank you. And now we have the next speaker with us on Zoom. So this is Victor Fargas-Ravu from Umeå University. So Victor received his PhD from the University of London and then spent some time in Umeå and then moved over to the US in Vanderbilt and then came back to Umeå again, where he is now. He will talk to us about a locally dependent version of the Harris-Kirsten theorem. So please, Victor.
Yeah. Thank you very much. So first, a technical request. Could you switch on co-hosting? All right. And now let me okay. So normally if everything has gone according to plan, you can now see my slides. Is that the case? No? So let me try again. Can you see my slides now?
I can see your slides, okay.
And can you see if I move? Yeah. No, you can't. All right. So. So we practiced setting this up and this still doesn't work. Let me try once more. And now let's switch to, can you see my slides now? No, that's still small.
No, we can see you. It's just that the screen here in Sigban is not really large, but we see you. So you can start your lecture. Okay.
All right. So there's a lag on the feed. So let me try to speak now and hopefully it'll work out. So thank you very much for the invitation. It's a real pleasure to speak in Uppsala, even if only virtually. And it's a rather daunting honor to speak after the Svante and Christina, who's given excellent lectures. So I will do my best to follow up on their talks by telling you about one of my favorite problems, which I think is deserving of more attention. This is also a problem that will involve random graphs. Trees will surface at one point in the talk. This will be a problem about random graphs and discrete probability with a kind of extremal twist in keeping with my own research interests. Okay. Oh. And yes, this thing doesn't work. My apologies. Can you see my? Does something happen when I move change my slides or not? Okay, right. Okay. So before I can tell you about this problem, I need to make a few definitions, and I'm very grateful that Svante and Christina have already given you some of these definitions. But in case someone has just tuned in, let me say very quickly that I'll be speaking about graphs. And a graph for a mathematician is a pair of sets, VE, V is a set of vertices, and E is a set of pairs of vertices which form the edges of the graph. And as Svante and Christina have both said, graphs are important outside mathematics because they're the mathematical model for networks. So the real world around us is full of networks. I'm doing my best to speak to you right now via a communication network. You might have taken a transportation network to attend this lecture. If you have friends, which I hope you do, then you're part of a social network. And as soon as you start thinking about a network in a slightly formal way, you start thinking about a graph. Within mathematics, graphs are also ubiquitous. They crop up in number theory, in group theory, in probability theory, in combinatorics. So many, many applications, and they really are fundamental objects. And when one studies graphs, one is often interested in the component structure and the connectivity properties of the graphs. So I won't define these formally, but let me just pull up two pictures. So here's a nice graph, the Peaches graph. The vertices are the blue balls and the edges are these black line segments. And this is a connected graph, forms one single connected component because I can get from any vertex I choose to any other vertex just by following the path of edges in the graph. Okay. And here's another graph which is not connected. It has 6 distinct components, each of which consists of an edge joining 2 vertices. And this kind of graph, which consists of disjoint edges, is called a matching. Okay. Okay. So I won't be speaking just about graphs. I'll be speaking about random graphs. And let me start by speaking about maybe the simplest random graph model of them all, namely the the p-random, the Bernoulli calculation model. So given a host graph H and some probability P between 0 and 1, a p-random subgraph of my host graph H is obtained by declaring open or including each edge of H independently at random with probability P. And you've just seen this model in Svante's talk. So if your host graph is Kn, the complete graph on n vertices, then the model I've just described above is the Erdős-Rényi random graph model. Namely, you have n vertices, and each possible edge is included with probability P independently of all the others. And this is usually generated by GNP. Right. So the study of this p-random subgraph model is known in general as Bernoulli percolation. And so whenever I'll say the word Bernoulli later on in this talk, I will mean exactly this kind of situation where each edge is included independently at random with probability P. Okay. So in this talk, rather than looking at Bernoulli percolation on the finite graph Kn, I'll be interested in Bernoulli percolation on an infinite host graph. So my host graph H will be Z square, the square integer lattice. And we're looking at p-random subgraphs of that. So the square integer lattice, that's just an infinite square lattice. The vertices are the corners of the squares and the edges of the sides of the squares. So the study of p-random subgraphs of Z squared, that was initiated by Broadbent and Hannity in Oxford in the late 50s, which is coincidentally right around the time when Erdős and Rényi started looking at their random graph models. So you could say there was something random in the air just before the 60s got started. And their motivation was modeling the movement of a fluid through a porous medium. But of course, the model I'm talking about is quite far removed from this kind of physical motivation. It's really a toy model for that. But the word percolation really comes from this motivation. If you imagine that the edges which are open, they're like pipes through which liquid can flow, and the edges which are closed are, well, pipes which are clogged somehow. And so when you study percolation theory, you study the ability of a fluid to somehow percolate through your random graph. Okay. So here are some pictures of how this can look like. So I've cut out a small box from Z squared, which is an infinite graph. Cut off a small square box. And when my edge probability P is 0.1, then each edge is open with probability, 0.1, so 10%. And so the open edges are in bolds, and you can see that there are a few of them scattered around, but they're quite far apart. When you increase the edge probability a little bit, you start seeing some slightly larger components. There's a little more of percolation which can happen. And then if you keep increasing P, eventually something dramatic will happen. And suddenly you'll have an enormous component which covers quite a bit of your finite box, which will arise. And this drastic change is the subject of one of the most beautiful theorems of probability theory, in my opinion. I'm sure others may have other opinion. But this is the celebrated Harris-Keston theorem. And it states that if we play this game of looking at P random subgraphs of Z square, the square integer lattice, then each edge being open probability P independently at random, if your edge probability P is at most a half, then all components in your random subgraph, all components of open edges will be finite. But if P is strictly bigger than a half, then in fact there would be an infinite connected component of open edges. And you can show this is unique. So Harris in 1960 proved this part of the statement, the zero part, and Keston proved somehow the one part, the existence of the giant, of the infinite component. And you can think of this as a kind of analog of the phase transition phenomenon that Svante talked about in his lecture in the context of the Edwards-Radian random graph, where you went from having all components being small to having suddenly a giant component. Except here, giant in our context means infinite. And so the location of this phase transition, P equals a half, is known as the Harris critical probability for Bernoulli percolation on Z squared. Right. So proving the Harris-Keston theorem is non-trivial and does rely on some fairly specific properties of the host graph Z squared, which I won't talk about. But the consequence of this is that if your favorite lattice isn't Z squared and isn't one of like a handful of other examples, and you ask me, okay, what is a critical probability for percolation, for Bernoulli percolation on that lattice? Then I can't just tweak the proof of the Harris-Keston theorem and answer your question. I just can't do that. Also, if you think back to the original motivation of Broadbent and Hammersley, the independence of the edge states in the model is not super realistic, right? In a physical environment, you do expect some local dependencies between edges. You expect that nearby edges somehow affect each other, maybe. So this leads to two natural questions. One is, how can we obtain some good rigorous estimates for critical probabilities on other host graphs H than Z squared, the square integer lattice? And also, can we develop some sort of locally dependent version of the lovely Harris-Keston theorem? And it turns out that these questions are related, as I will show you next. So to do so, let me introduce the notion about one dependent random graph model. So I'll start with a random graph H. Now, and now I'll look at it at a more general way of generating random subgraphs of H, rather than just flipping an edge for flipping a coin for each edge independently and random. So let me consider probability measure mu on the subsets of the H set of H. Well, using that, if I got something like that, then I can immediately build a random graph model, just select a subset of edges at random according to the distribution given by mu, and you get a random graph, like H mu. I call this the mu random graph. Now, I'm not interested in all random graphs get generated in this way, but in a subclass which has some very weak local dependence. Explicitly, I'll be interested in the class of one-dependent models. So these are, and from now on, by the way, I'll say model and random graph and probability measure interchangeably. So apologies about that ahead of time, but they're basically the same thing as far as I'm concerned. So the probability measure, or if you prefer a random graph model mu, is one dependent if whenever I have two sets of edges in my host graph H, which are vertexes joined, so they live on different sets of vertices, then the state of edges in A, whether they're open or closed, is going to be independent from the state of edges in B, open or closed, in my random graph. So maybe here's a picture which can explain what I mean. Here you have a red set of edges and a blue set of edges. And now suppose I have a one-dependent model on this kind of grid graph. Well, then what happens inside the red edges doesn't tell me anything about what happens inside the set of blue edges. Knowing that this particular edge is open doesn't tell me anything about these blue edges, because these two sets are vertex disjoint. On the other hand, my two sets of edges look like this, then there's the red edges could potentially tell me something about the blue edges, because there's a vertex which is in both the red edge and the blue edge. So for example, knowing that this red edge here is open, it might tell me that this blue edge is more likely to be open, for example. Okay. And a good way to think about one-dependent models is informally that these are models where the randomness resides inside the vertices. So how the randomness comes from the vertices, and therefore what happens inside disjoint sets of vertices is independent. Okay. So let me introduce some more notation. I'll use write a 1 dpm on H for a one-dependent probability measure or a one-dependent random graph model on my favorite host graph H. And then write M1P of H for the collection of all one-dependent models for which each edge is open with probability P. So this is going to be my one-dependent analog of Bernoulli percolation with edge probability P. But there's an important difference, right? There's only one model for Bernoulli percolation. There's only one way of independently declaring each edge open with probability P. The key difference is that the class M1P of H of all one-dependent models is extremely rich. There are lots and lots of measures that live in there, and there's actually no convenient way of enumerating them all. Well, you can't enumerate them because there are infinitely many of them, but there isn't a good way of understanding this class of measures at the moment, unless you have a very, very small graph H. So let me give you some examples of the kind of models you can find inside this class. And a nice example is that of side percolation. So in side percolation, you build a random graph on your host graph H as follows. You switch each vertex on with some probability theta, independently of all the other vertices. And then you declare an edge to be open if both of its endpoints are switched on. Okay, so this is going to be a one-dependent model because all of the randomness comes from the vertices. What happens in disjoint sets is going to be completely independent. And what's the probability that an edge is open? Well, for an edge to be open, both of its endpoints need to be switched on, which happens with probability theta squared. So you get theta equals square root of p, you get a one-dependent model in which the edge probability is exactly p. Okay. And this is a good example because it tells you what kind of things you can build. So more generally, if you want to run with this example, you could build a random graph on your host graph H by assigning to each vertex some random color, say, according to your favorite distribution, and then declaring an edge to be open according to some deterministic rule, depending only on the color of its endpoints. And so there's a huge number of ways of doing this. So this M1P of H, this class of one-dependent models, is extremely rich, which provides us with a significant challenge. And now this brings us to the problem I wanted to tell you about, namely the one-dependent Harris-Keston problem. So if you cast our mind back to the Harris-Keston theorem, which I stated earlier in this talk, the Keston part of the theorem essentially said the following. If you have a random graph model on the square integer lattice, in which the edge probability P is strictly bigger than a half, and each edge is open independently at random, independently of all the other edges, then you have percolation Z square, that is, you have the existence of an infinite connected components of open edges. So the question I'm interested in is, what if you only have one dependence rather than full independence? So what if you have edges which share a vertex can influence each other, can somehow conspire together, and maybe try to work together to prevent the appearance of an infinite connected component? So this question first arose in the work of Ballister, Bolobash, and Walters in 2005, and is wide open. So to make it a little bit more formal, what I'm asking about is finding some one-dependent analog of the critical probability for percolation. So I want to define to determine P1C of Z squared, the smallest p, so that every one dependent random graph model on the square integer lattice Z squared must contain an infinite connected component of open edges with probability 1. Okay. And now in the few minutes I have left, I will try to tell you very quickly what's known about this problem. First, I will tell you why we should care about it, namely the method of Balster, Bolbach, and Walters. So they came up with a very cunning way of giving rigorous confidence interval estimates of critical probabilities for a host of random graph models on infinite lattices and also continuum percolation models. So basically think of yourself, think of having a huge number of models where you'd like to know essentially when the phase transition occurs. And Balster, Bolbach, and Walters can give you a rigorous way of estimating when that happens by comparing your model to a one-dependent random graph model on Z squared. And so a consequence of their method is that if you have improved estimates for this one-dependent critical probability, in particular if you have better upper bounds for it, then you can get better confidence intervals and better estimates. Of course, the local dependencies also provide some interesting technical challenges. If you're interested in probability theory, you might care about this one-dependent Harris-Kessler problem because it leads to some interesting questions about things like the Lovász local lemma. And as for myself, one of the reasons I'm interested in this problem is that it's a beautiful extremal question. So what do I mean by extremal? Well, in the Harris-Kessler theorem, you just ask, is there an infinite component or not? Now in the one-dependent Harris-Kessler problem, you're asking actually for something slightly different. You're morally asking, what is the worst one-dependent model for percolation, for the existence of an infinite component? How can I arrange for edges to conspire together locally to prevent this global phenomenon that is the existence of an infinite component? So it's a very extreme, a very appealing question from the point of view of an extremal combinatorialist, which is how I got into this. And this question is wide open. So in terms of the upper bounds, it followed for some work of Liggett, Shulman, and Stacey in the late 90s that this one-dependent critical probability is strictly less than 1. An effective upper bound of 0.8639 was provided by Balster, Bolbach, and Walters using a very cute renormalization arguments, which unfortunately I can't give you here. But they noted in the paper that they could not even hazard a guess as to the correct value of this one-dependent critical probability. In 2012, Balster and Bolbach determined critical probabilities for the phase transition for one-dependent percolation on infinite trees, providing some one-dependent analogs of some results of Russell-Lyons. And they again turned back to this problem of determining P1C of Z squared, this one-dependent critical probability for percolation Z squared. And they noted that giving a good upper bound for this is surprisingly difficult. And unfortunately, as far as the upper bound is concerned, this is where the problem has stayed here. There's been no improvements since 2005, which is a while now. So what about low bounds? Well, let me quickly show a trivial low bound we can give. So let us construct a random graph, a one-dependent random graph on Z squared, which doesn't percolate. So we'll do that by randomly calling vertices in Z squared. So each vertex will be assigned a color independently of all the others, and we'll color the vertices as follows. So the origin will be colored red with probability 1. And then the ring around the origin, the infinity ring around the origin, will color vertices blue with probability 1/2, red with probability 1/2. The next ring will color every vertex blue. In the next ring, we'll color blue with probability 1/2, red with probability 1/2. In the next ring, we'll color red with probability 1, and then we just repeat and extend infinitely, so we'll ripple outwards in this way. So this gives me a random coloring of the vertices of Z squared. And now I'll declare an edge to be open if its endpoints are the same color. So because all my randomness comes from my vertices, this is clearly a one-dependent model. And it's easy to check that the probability that an edge is open is at least 1/2, right? Exactly 1/2 if you go inside one of these rings. So one half from a red ring to a red-blue ring. So if you kind of thin appropriately inside the blue ring, you do get one append model that is inside the set. And in this model, it's clear that you can never, there's no open path from a red ring that sort of crosses a blue ring. So every component somehow lives squashed between either two red rings or two blue rings, and in particular is finite. So this trivial construction shows you that the one dependent critical probability for z squared is at least 1/2 using this trivial construction. Now, of course, we already knew this from the Harris-Keston theorem, because Bernoulli percolation is itself one dependent. I mean, here the edges just don't conspire with each other. But this is a very heavy hammer when a trivial construction would do. So you can do a little bit better than this, but using a similar sort of idea and the kind of side percolation model I talked about earlier, you can actually get a slightly better construction which creeps up above 0.5. So I don't want to say too much about this, but let me just say that you can certainly use the local dependence between the edges to delay the global phenomenon of percolation z squared. And since I'm running out of time, let me maybe finish by saying that with my postdoc Nick Day and visiting PhD student Robert Hancock, we improved the low bound construction to, we actually gave two different constructions. First, we gave a certain kind of 4-ring construction to show that this critical probability is at least 4 minus 2 square root of 3, like 0.5359 something. And then using a side percolation twist, you can actually raise it a little bit further. And so if you believe some certain simulation estimates, maybe our construction gives a low bound as large as 0.5549, which is significantly above 1/2. And the key here was a 4-ring construction, a kind of extension of the really trivial 3-ring construction I showed you. This is something which dates back actually to my PhD thesis. So you have the basic one, you have a kind of a sneaky coloring that involves 4 rings, 3 colors, and some slightly complicated optimization, but that's from which you can build a measure that doesn't percolate. And because this construction is asymmetric, I was, and just use one more ring than the trivial construction, I was initially inclined to completely dismiss it as being a kind of irrelevance. But as time has gone on, and especially due to recent work of mine with Vincent Fenninger, I've come around more and more to the feeling that this measure isn't actually, despite the fact that it's so slightly weird, this measure is actually meaningful, says something meaningful about one-dependent population. It is universal in certain ways, which I probably won't have the time to tell you about. So maybe to kind of finish my talk, let me just say that there are lots of open problems around this problem of locally dependent population. And of course, the major problem is improving the upper bounds of this silly 0.8639 I showed you. But maybe the big difference now, as of like last spring, compared to when Ballas and Bolobash, for example, were working in 2012, is that now I think there is some reasonably convincing evidence that the correct value of this critical probability should be quite close to the low bounds, and maybe even around, so yeah, well, maybe even less than 0.6. So I think my feeling is definitely that the upper bound is off by miles, and this is definitely a nice problem that could do with some improvements. And I think I will stop there and just say that there's some nice problems which will require a mixture of tools from probability theory and combinatorics. So if any of you bright minds in Uppsala have ideas, come and talk to me in Umeå, and my brain is open. Thank you very much for your attention.
Thank you, Victor. Thank you. In the interest of time, I think we'll skip questions for just a few seconds, so you can ask questions for Victor or to Svante or Christina. So I'll ask Svante and Christina to come here. And then you can zoom out a little bit as well if you want, and we can talk about the general topics, I would say. So while Svante and Christina is setting up. If there are any questions for Victor while they're getting in place, just feel free to fire away.
Actually, I had a question for Svante and Christina, which I can ask maybe. Can they hear me?
Yep, we can hear you.
Yeah. First, thanks for the lovely talks. One thing which actually made me slightly curious is that so you can use depth first search and random trees to explore basically graphs, right? So is there a way of using something like a continuum Brownian tree to explore some random region inside R squared?
Not that I know of. I think that looking in the plane means that you get a completely different kind of geometry. The geometric effects there. Okay, I'll hold them. The geometric effects, if you do something in a plane, will make things very different. You can say in some sense the Brownian trio and Edwards-Renyi graphs and so on, they don't have any geometry. You could say they're somehow how more related to infinite dimensional situation. But the low dimensional geometry is very different, I think. What's your?
Yeah, I agree completely. I think, I mean, it's sort of, maybe my talk was a little bit misleading in some sense in that I was drawing everything in the plane, but that was really just for my convenience, if I can put it that way. The Brownian continuum random tree doesn't really live in the plane, really. I mean, we think of it as a sort of abstract metric space, and so one can think about ways of sort of trying to embed it in the plane, but that's a sort of different question.
It was just Svante's comment about depth first search, and I was thinking, would it be if you drop me in a random, like let's say, close connected region inside R squared, bounded, how quickly could I work out what my region is like or how large it is? And I guess I would try to walk around at random until I hit the boundary, and then, well, I guess I could follow the boundary then once I found it. So that's probably the smart thing to do. But maybe the boundary could be very long. So if I want to get a good idea, I could just try to walk the boundary, then get back to the center. That was just a thought.
Yes. Well, I don't know anything, and said my feeling is that you can do, for example, depth first search, or certainly in a plane network, and my feeling is that it will be something different there, but I don't know what it will be.
Yeah.
Victor, I have a question for you, if I may, from your talk. So you said at the end that you thought that the correct answer for this was really close to your bound that you've got, which is sort of 0.55-ish or something like that.
Yeah.
Can you say a little bit more about what it is that leads you to believe that that's the correct answer, rather than the sort of upper bound given by balance?
Right. Yeah. Okay. Yeah. Thanks a lot. Yeah. Sorry for rushing towards the end.
No, that's fine.
So the reason is that basically we looked at the reason I think that this low bound may be close to tight is with Vincent Fenninger, who was visiting PhD student in Umeå last spring, we looked at one dependent percolation on d-dimensional lattices, right? So you have more rooms, it gets easier to percolate to form an infinite components. So you ask, okay, what's the limit as d tends towards infinity of the one dependent critical probability for percolation z to the d? And so this weird four-ring measure, which I haven't put up, actually gives you a low bound for that. In fact, it gives a low bound for one dependent percolation on any of a huge family of graphs. And in some cases, we could show that this was the correct answer. So if you look at percolation on the Cartesian product of z squared with a complete graph on n vertices, and that tends towards infinity, then the critical probability for that goes to 4 minus 2 squared root of 3. And it involves a little probability, but there's also some extreme graph theory that goes into here that essentially shows that this weird four-ring construction, which is asymmetric, actually turns out to be optimal in some sense. And it turns out to be the unique optimum. And in fact, we don't need all of Kn. I can just replace a complete graph by a pseudo-random graph with density roughly log n of ren, and it still works. And so my feeling is that as soon as you give me a little bit more space than z squared, that this 4 minus 2 squared root of 3 should probably kick in. And so probably even in z squared, you shouldn't be able to do much better than that.
Thank you.
Sorry.
Any questions from the audience?
Is there a trivial argument telling you that it must be more than a half?
Could you repeat your question?
Sorry. The one depends.
That your lower bound must be greater than a half. Is there a trivial argument? I mean,
Yeah.
this is not my field, so it may be
Yeah.
a silly question, but is it
Yeah,
obvious that it must be more than a half?
It's a good question, and then the answer is this like slightly trivial 3-ring coloring. So you color the origin ring, red. Then you look at like a d-dimensional ball around the origin. You call that blue or red with probability half. Then you look at the next ball. So you have like an infinite sequence of layers. You color red. The next layer red or blue with probability half. Next layer entirely blue, and you kind of repeat. And so since you can never go from a red vertex to a blue vertex, you're always trapped between like 2 layers of this sort of infinite onion, if you see what I mean. So if you contain a red vertex, you're trapped between 2 blue layers of your infinite onion. And if you contain a blue vertex, you're trapped between 2 red layers of your infinite onion. And that's why you can't do better than a half. So you can't, a half is a trivial lower bound.
Okay, that shows that it's at least a half, but is there some similar way to show that it's strictly greater by twisting this, or do you have to work hard to show that?
No, so this is this thing which I swept under the carpet at the very end of my talk, for which I apologize profusely. So this tweak, this sort of weird construction on 4 rings. So you use like one more, you use one more color and you do something slightly different, and that suddenly gives you a low bound of 4 minus 2 squared root of 3 for basically almost any a huge number of graphs you could think of, including the d-dimensional lattices. Which is maybe slightly surprising.
Okay, I have another question for Victor also. You talked about one dependent percolation. Is there any significant difference if is the weakening to 2 dependent or more generally other fixed distance? So say that, for example, you have independence for any 2 sets of edges which are of distance, say at least 10 from each other.
That's an excellent question. I had thought about putting this among the open questions. It's a very good question, and there basically you can show that this critical probability will be strictly less than 1 by renormalization arguments. And you can show it's bigger than, again, 4 minus 2 squared root of 3, but there you should be able to do something better. I'm sure that there should be a 5-ring construction or something for if you require like more dependence. However, I don't think anyone has looked at that. That's a completely open and a very interesting question. I can say that as more dependence you allow me, the more I can push up like the critical probability for percolation. But the bounds, I think, are pretty terrible.
Thanks a lot. Before we end, speaking of open questions, so maybe we can try and zoom out massively, and let's say that you have a new bright person starting up their PhD. So where would you send them off, given this point in time and the fact that they have not studied these objects for so long? Where would you send them?
Well, why send them somewhere? Why not stay here?
In terms of problems to look at, they can stay here for sure.
Yeah, I would absolutely tell them to go to Uppsala or Oxford.
Oxford is not a good university, no doubt.
All right, in terms of topics then. on random graphs, what would you? What are the most pressing ones in terms of what has a chance of having a big breakthrough in 5-10 years?
Well, I don't think I dare to predict. It's difficult to predict the future, but I think that this area in general is something which is very much alive now. Both Christina and I chose to talk about some basic things that are well known and sometimes rather old, but this area in general is very active and a lot of people working on different problems there. So I think that is a good area to work on. Of course, that means that you will also face a lot of competition from others, maybe doing the same thing at some other place if you're unlucky.
I mean, perhaps I can make a more general comment, which is this notion of a scaling limit is of enormous importance in probability generally. You know, I mean, in percolation also, you know, in the situation where you have an underlying lattice, you know, there's massive progress in 2 dimensions in studying what sort of critical statistical mechanical models look like in their scaling limit. So this is where this Schramm-Loewener evolution theory comes in. But, you know, in the context of random graphs, you know, the Brownian continuum random tree is really the first scaling limit for a random graph, and that's only sort of 1990. So this is quite a young field in some sense. And okay, there is a fair amount of kind of stuff to learn before you can get into it, but it's also relying on quite classical stuff. I mean, you know, lots of the things I talked about in my talk and that were sort of deliberately done really are kind of classical topics in probability theory. So, you know, a graduate student in probability would, you know about a Brownian motion, would know about these EARN models. And okay, maybe you don't have all of those tools at your disposal at the start of a PhD, but these are kind of things which is kind of, you know, there exist courses that one can learn about these things in. So it's not so far away from what a sort of beginning graduate student can get their teeth into. So maybe a question for Svante, sort of an interesting model. So we have these inhomogeneous random graph models, which Svante in particular has studied quite extensively. And the situation where we understand the scaling limits at criticality quite well are these rank 1 models, where essentially you've got these sort of product forms for edge probabilities. Do you think there's scope for proving scaling limits outside of that class?
Well, again, it's difficult to say. Certainly, I don't see how to do it, but on the other hand, there's been a lot of progress in mathematics, things I didn't know how to do. So I wouldn't be surprised if someone finds some way of doing it, maybe in some unexpected way. That could be something for a future bright PhD student you asked about. But it would be a high-risk project. It may be that there just isn't any good answer in general, but I don't think one should rule out the possibility.
Very good. Thanks a lot. Thanks a lot. It's late. It's time for us to close the session.